Sorry, everybody, forgot to record that, so we're going to go ahead and start recording that, but you didn't miss anything in terms of the problems quite yet. But we've got this truck driving away. We got a squared plus b squared equals c squared. Now we've got to do some implicit derivative. So what is the derivative of a squared, everybody? 2a dA dt. So that's very, very, very important, that dA dt part, because we're always taking the derivative with respect to time. And then the next one would be 2b dB dt, and 2c dC dt. That's fun. So I did my calculus. Now, can I start plugging some data in? What do we know already? Do we know dA dt? What is dA dt? Read the story. This truck A, drives at 40 miles an hour. Now, by the way, that should be dA dt, right? Plus, I'm going to put a parentheses there. I'm going to put a parentheses right there, and I've got dB dt because that other truck is driving 30 miles an hour equals, I don't have enough room. Now, dC dt is actually the thing that I wanted to find. Now, you might have noticed that I dropped the 2. Why? Didn't they all have one? So could I just divide that 2 out early in the stage and not even worry about it? Okay, so here's the thing. 6 minutes later, that was done on purpose. How much of an hour is 6 minutes precisely? 1/10 of an hour. That was very much on purpose. So in 1/10 of an hour, how far will this truck have traveled? 4 miles. You're welcome. In 1/10 of an hour, how far will that truck have traveled? I hope this makes you smile, because if that's 3 and that one's 4, you're welcome. That was a 3, 4, 5 triangle. So what values in my equation did I just give you? A, B, and C. So we know that A, this guy down here, was 4. This one was 3. And this one was 5. And what's the only thing up here we don't yet know? dC dt, right? So I got 160 plus 90 equals 5 dC dt. Now, unlike in physics, frequently what we do is we'll drop the units for a moment and then we'll put them back in. Okay? So what do we have then? 250 divided by 5 is 50. So dC dt equals 50. So the one thing that I haven't completely gotten to is at the very, very end of all of these word problems, you're supposed to make a summary statement. So 6 minutes after the intersection, the 2 trucks are, well, I should say the distance between the 2 trucks is increasing. Now, by the way, why is it increasing? Because that derivative is positive. Increasing at what rate? Miles an hour, right? Does that mean that the trucks are driving 50 miles an hour? No, one's driving 30 and one's driving 40. So, interestingly enough, so could a police officer actually gauge you while they are driving themselves? Yes, they can. Does it get a little complicated if they try? Because doesn't that look like, hey, you're speeding, you're in a 40-mile-an-hour zone, I got you going 50. And you're like, no, you don't. My father-in-law is the kind of person that would take them to court over that, because I've seen him do it. Do you know that the police officer technically has to see your tires if they're going to say that you rolled the stop sign? Because it's not that your car has to stop, it's that your tires have to stop. Well, what happens when you stop your car? Doesn't it still lurch forward just a little bit, even if your tires stop? It's just a momentum. So that was funny. He got out of one of those tickets, which he knew he was guilty on, but he could prove that the cop couldn't because there was one of those big berms that was there, and the cop could not possibly see his tires because of one of those road barrier things. It's like, dang. I think he also got out of another one because he subpoenaed the records on the radar, because you have to calibrate them occasionally. And he was able to prove very quickly that they hadn't calibrated it within the amount of time that you're supposed to calibrate the gun. You know, it's like the legality, you have to do it every 2 months, and they hadn't done it in like 4, so it got tossed. I gotta learn some of his tricks sometimes. Sometimes the cop is just like, man, you're a jerk. And he's like, yeah, but I'm not paying insurance. Okay. All right. So, anyway. So here we go. That's funny. That's funny right there. Okay. All right. Now, do you like my guys here? I think they're pretty cool looking guys. Okay. So 2 guys are walking away from each other. Now, what makes this problem a smidge harder than the previous one is that these 2 people are actually walking away from each other at precisely a 60-degree angle. Maybe it's one of those roads in San Francisco that don't come in perfect 90s. They're just like, a little frustrating. So I know that I've got this 60-degree angle, which at least that one piece is a constant, which, by the way, yes, this is calculus. Let's call that pi over 3. So our pedestrians probably don't know that, but we do. So let's call this one A, this B, and this C. And let's resist the urge to use the Pythagorean theorem, because that, ladies and gentlemen, would not be accurate, because this is not a 90-degree angle. So let's see if anybody remembers what we could use to solve triangles that are not right triangles. I heard 1/2 base times height, but I don't think, we want to find out this distance right here. Chop it in half. What? What am I chopping in half? Ooh. That's a cute idea. But because they're walking at different paces, where that 90 would be changing. And that's, now you're getting complicated, because I now have to come up with a crazy polynomial expression to describe where that 90-degree happens at any moment in time. That sounds a little tough for me. Let's not do that one. So let's go back and do your favorite and mine, the law of cosines. The law of cosines says that c squared in any triangle is a squared plus b squared minus 2ab cosine of c. That was the law of cosines. It's been a minute since we've done that. In fact, that happened, oh goodness, that happened, probably about the first week of March, right before the world ended. It's about right, isn't it? So, okay, so how the law of cosines works is you say the hypotenuse, which is not really a hypotenuse, that side squared is equal to the sum of the other two, and then there's a qualifier, 2ab cosine of that angle in the middle. But one thing that we talked about is because of the fact that you can use constants early, is this a constant in my problem? Yes, it is. So guys, what is the cosine of pi over 3? The cosine of pi over 3 is a half, dead on. It's a constant. So the cosine of pi over 3 is a half, it's a constant, I could put it in. So if this is a half, what's gonna happen to that half with that 2 right there? You're welcome. That's why I picked 60 degrees. So we've got c squared equals a squared plus b squared minus ab. Now, if that was not specifically a 60-degree angle, this would be a much harder problem. I picked that one, so that would actually make that a little bit better. So now here we go. What's the derivative of the c squared part? 2c times dc dt equals 2a times dA dt plus 2b times dB dt. Man, that's a tongue twister. Oh, man. Now what? Minus dA dtb minus dB dTA. Oh, that's obnoxious. Did you guys catch I had to use a product rule there, didn't I? We got a product rule at bay. Okay, all right, that's fine. That looks terrible. How many things do we know? No, seriously, look, what do we know right now? Well, let's see. It says the two roads are at 60. The man starts at 1 p.m. Oh, that's strangely specific. This is what I was telling Pelinconi, that we were going to do all of the things that they mock math teachers for doing. We've got the whole thing. I'm embracing it. At 3 miles an hour. So this guy, let's call this one, starts at 1 p.m. at 1 p.m. at 3 miles an hour. So what happened to this guy right here? He starts an hour later, and he is walking at 4 miles an hour. So at 4 p.m., let's talk about what happens. Okay, so this dude right here left at 1. So how long has he been walking for? He's been walking for 3 hours. So at this moment, he's actually 9 miles down the road. He is probably getting a little bit tired. Okay? If it was my brother, he'd just be starting his jog. Okay, this guy is going a little faster, but how long has he been at it? Just for 2 hours, so he's actually gone 8. Now, one of the things I'm trying to model with you is, when did I plug those things in? Honestly, it's after I did the calculus. One of the things that people want to do is they want to plug those numbers in early. What happens if you plug them in early? Their derivatives become 0, and then you lose the data that you're needing to get. So let's talk about what we have. What does the 9 represent? 9 is, in my word right here, 9 is A. What is the 3 miles an hour? That's dA dt, which is right here, just looks really sloppy. What is B? 8, and dB dt is 4. Do we have everything that there is to have in this problem except for one and only one piece? Almost. Do we have C yet? Dang. But could we use this formula right here to go find what C is? We can. So let's do that. So at this moment, I know that C squared is A squared plus B squared minus AB. And keep in mind, I normally put that cosine in, but in this case, I knew that the cosine was 5 or 6, so I didn't have to. So let's see. I got 64. I got 81. And I lost 72 for a total of 73. So what does 73 represent? Oh, I forgot to take the root. Thank you. Square root of 73 then represents what C is, which I'm just going to leave it. All right, so can you guys go get that for me? Plug it in. See if you can actually accurately come up with what dC dt is. I gave you all the pieces. You should be able to come up with dC dt. watch those letters. Oh, booger. I got about 29 over root 73 when I did mine. Did you guys get 58 out of all this junk over here? Yeah, so 58 over 2 of those, 58 and the 2 cancel, leave 29. Now you're supposed to write a sentence, I just don't want to. But like if you're taking a test, you say at this particular moment in time, the 2 people are moving. Does it make sense that it's 3.9? This guy's doing 3, that one's doing 4. It kind of makes sense that it's something in the middle because we're losing a little bit of that area because they're going the same direction. Are you guys doing okay so far? So, okay, here we go, everybody. Yeah. This one you need a star on. And honestly, this is the one I've been waiting to get to because I needed you to see it. This is the pet problem of every calculus teacher in every calculus class that has ever existed and shows up on AP tests all the freaking time. Okay, so you need to be aware that this is considered a pretty darn significant problem because of something that happens in here. So we have the snow cone here. We've got this cone, and somebody's going to pour water into this snow cone at a constant rate, and we want to find the rate of change of the height and the radius as it goes up. Now, if you think about it, what is happening as the snow cone fills up? Is the height of the cone changing? Really? So we've got this cone like this, right? As we start pouring the liquid into the cone, is the depth of that liquid going to be changing over time? I think you would agree that there is a change, right? Would the radius of the liquid at that height be changing as well? Oh yeah. So in other words, in this case, unlike the one that we did last week where it was a cylinder and the radius stayed constant, what's happening here, everybody? It ain't changing. But there is something that's really super helpful in this problem. When we set this up, it's going to look like we have way too many variables. I'll just warn you in advance. It's going to look bad. But there's something that happened here. What is the height of our cone? It's 20, isn't it? Centimeters. What is the radius of my cone? 4 centimeters. Now here's the thing. True or false? This triangle right there at that juncture is similar to the big triangle. Okay, welcome back to Math 2 for a second. If you ever have 2 triangles that are similar, then their sides are proportional. Right now, everybody, what is the ratio of the radius to the height? What's that? It's 1 over 5, isn't it? Can't we come off here the side that say that the ratio of the radius to the height is always going to be a perfect 1 to 5 ratio no matter where it is? So when we do this problem, right off the bat, we're going to have a little bit of a problem because we're going to have way too many variables in this problem. But what I'm telling you that I can do right away is what can I replace every h with? 5r. What will that do to my number of variables in my story? It's going to shrink them down. So let's talk about the volume. I did give this to you last week. You may not remember it. Anybody remember the volume of a cone? Volume of a cone is 1/3 pi r squared. That should look familiar. What is pi r squared? That's our circle, because of course the base of this cone is a circle. Darn it, I got to change colors. My pen just ran out of ink. Times h. But what did we just say that we could do for fun? Can we replace h right now with 5r? Would that make our life a little bit better? Oh, not just a little bit, it's way better. I'm going to replace this one with 5r. So this problem that was probably going to be very, very complicated isn't. So what is the derivative of this side? dv dt. The volume is changing with respect to time. What about the derivative of the other side? You're welcome. 5 pi r squared dr dt. Don't forget your implicit derivatives. Okay, we've got it. Now let's look at the story, what it says. Find the rate of change when the height is 10. Dang it. So if they're telling me when the height is 10, did they tell me what the radius is? What is it? It's 2, because we knew this had to be at a perfect ratio between them. So let's see. Let's talk about what we know. Do we know dv dt? Water's being poured in at 8 cubic centimeters a minute. What is that? That's volume. That's dv dt. That's 8. Do you guys know what r is right now? It was 2. It asked me for the rate of change of the height and the radius. Can we find the rate of change of the radius right now? What's left? Divide. That's it, right? dr dt. So let's see if you can figure it out. What is dr dt? What's 2 squared times 5 pi? I think that's 20 pi, isn't it? So if I had 8 over 20 pi, we should reduce that at least a smidge. They're both divisible by 4, so 2 over 5 pi. 2 over 5 pi what? What's the units? Centimeters per minute. So at that particular moment, it's growing at exactly 2 centimeters per minute. Okay, now here's the fun part, because it's actually so stinking easy. See this equation? Is this a valid equation? Right here. For this story, will 5 radii also always be the height? Well, guess what that means then? 5 dr dt's is a dh dt, isn't it? See, if I took the derivative of this, which we know to be true, 5 dr dt's is a dh dt. So what do we know already? I know dr dt. So do I know dh dt? What do I have to do to it? Multiply it by 5. So if this is 2 over 5 pi, then what's the other one if I multiply it by 5? 2 over pi. 2 over pi centimeters per minute is dh dt. And we just did a pretty difficult problem. Now, in this cone thing, is that actually what really happens? Yeah, it does. Every single time you get similar triangles. So Quite literally, if you've ever been to a quarry, you guys ever notice like when they crush rock and they put it up that conveyor belt and it drops over and it hits the pile and it makes this big cone? Guess what? Does that happen? So you have a DVDT that's happening because they have a certain speed at which the rock is falling off of that. So could they actually figure out how fast the radius of that pile is going to change? Well, at first, it's going to change pretty quickly, isn't it? But over time, when the volume gets big, that little bit isn't going to create that much of a change. But they can kind of find out how fast the height and the base are changing. And they do need to know those things sometimes, because at a certain height, it's no longer safe. Because, well, if it came down, it might be a problem, right? If it lost a little bit of its tension. So the last problem that I was planning on doing with you is this one right here. Is that we've got somebody watching a balloon over here. And I know that as I watch the balloon, I could see with a clinometer. Do you guys know what a clinometer is? Some of you know what a clinometer is. Let me grab one. Okay, well, I thought I was going to grab one. I let Mr. Null borrow them and then I put them back somewhere. Anyway, it's this little device that basically you look through and it has a protractor and a straw on it and a string. And you can watch it and you can see how the angle. So I know when I'm watching this balloon over here that the angle that I'm viewing, I can see that it's going up at about a 0.14 radians a minute. So the question is, how fast is the actual balloon going up? I know that the radius, that the height is changing this way, but let's see, what do we know? So what is a relationship that I could use to establish between the height, 500, and theta? What is that simple ratio that I could use? Very simple ratio that relates these three features. You guys have to have this. SOHCAHTOA. Which one is it? It's been a minute. Which one involves this opposite guy? Oh, I think that's a tangent. The tangent is opposite over adjacent. So that's what I see. But this is what I want you guys to see is people like talk about related rates like they're just, oh my gosh, it's the hardest thing. Well, that's the hard, we just did the hard part. We wrote down an equation. Do you guys know how to find the derivative of a tangent? I hope so. That's secant squared, right? Do you know how to take the derivative of 1/500th of h? 1/500th of dh dt, right? So look at what I gave you. Did I give you some good stuff? Did I, what's in there that I already handed you? I gave you theta. Oh, hey, what is the secant of pi over 4? I know it's been a minute since you've done that. Do you guys remember what the cosine of pi over 4 was? It was root 2 over 2, but we're supposed to square that. So I'm going to write that over here. The cosine of pi over 4 is root 2 over 2. So what does that make the cosine squared of pi over 4? 2 over 4? In other words, a half. So what does that make the secant squared of that? 2. Cool. Okay, this one was 2. Do we know what d theta dt is? 0.14. Radians per minute. Equals 1/500th of dh dt. What are we trying to find, everybody, in this story? I want to know how fast the balloon is rising. What would that be? I think that would be dh dt. Now, if you were in a physics class and we religiously wrote all of the values in here, all the way through, what would happen? So I got 2 times 0.14 times 500 I got 140. Cool. 140 what? Okay, this is the fun part. It is technically radian feet per minute, isn't it? Wasn't that radian still in this problem? But what do we talk about radians? They're a quasi-unit. Remember that radians kind of appear and then they kind of disappear at will because they're just sort of a qualifier. So this balloon's going up at about 140 foot a minute, and that's the end of our story. So I have one more thing that we're going to look at later in the period, but for now we're good to go. So here's the deal. Back in 1953, Roger Price invented a minor art form called a droodle. You have seen that. The droodle that we did last week was like you had this little funny thing and then you came up with what it was called, right? Did you guys get your droodle? Anybody solve the droodle last week? It was the last thing you see from an annoyed elephant, and it's its foot like crushing you. That was the droodle. But what happens is a turvy actually is a droodle in two ways. So what happens is this has a story attached to it, but so does that. So the turvy, when you solve it, actually gets one way when you're looking at it right side up and a totally different answer when you're looking at it upside down. So you will see those things. So you're going to go through a series of related rates problems, which you should certainly work together on. Wait, what's that? I was here. Oh, okay. Okay. Did you not look on your Google Classroom? I didn't have time. All right. So enjoy, everybody. Now, so the droodle, I'll get you. I'm sorry. So here's what happened. This is actually kind of all review-based stuff, like what the derivative is for that's it. Or what the derivative is like zero. And anyway, you go through this thing and you fill out the letters and you put it all in here. And I think it's the last thing you see from an angry elephant. Because it's like, pressure. That's the dumb message. All right, so Amber, please let me know if I can assist in any way. You do not really have to print all of that out because you could just write them one at a time. So please understand this is not 14 questions, it's actually 7 questions because within each question you're getting 2 different things that they're going to ask you about. So it's not as long as it sounds. I'm not giving you 14 related rates problems. And yes, I do have an answer key. What's that? A ball? Snowball. Snowball. That'd be a fun snowball. It'd be heavy. Yeah, I guess if it's melting. So you have a snowball that has this as its diameter. That's impressive in this kind of ruin. I think that guy might be like one of the people from like Lord of the Rings. Maybe he's like a shot. That would be a compressionally heavy snowball. That's a boulder. That's a snow boulder. I like it. A snow boulder. I should rewrite this. Make it a snowball. Technically, it still is a snowball. It's just massive. And the person who did it, that was Andre the Giant, was the one that was throwing it. You guys even know who Andre the Giant is? His name says it all. He's He's a wrestler. He's freaking massive. Absolute unit is perfect. And his voice sounds like his like what you would imagine the voice of Andre the Giant. Yes. Yeah, he's in The Princess Bride.
Hey, Mr. Penner.
Yeah, that's Andre the Giant. Yes.
Do you think you could upload this the answer key in a bit?
Yes, I can.
All right, thank you.
That's what I was working on, is I was actually taking the answer key off of it because I didn't want people to see it too quick.
All right.
I can absolutely share that with you.
All right, thank you.
Yeah, no problem.
All right, see you tomorrow.
All right, see ya. See, what you guys may not realize is that when I did this thing with the trucks, I actually programmed those two trucks to have different speeds to match the question that we just did. So I actually made them in that ratio of their speeds. Well, it's kind of a pain. See all this work that I had to do to create that? I actually did all that from scratch. Mr. Tyler, it's going to be some things that are really great, but it's like it must be. I just enjoy it. I'm such a geek, honestly. When I thought about doing that, I got all excited. There's another one that I did. The lamppost.
Yeah, I'm on the Babylonians and Dungeons.
Yeah, I was to say Babylonians because it's an easy lens.
They're both ancient. They're both on the other side.
They could have done it at the same time. What's actually he's laughing, but because I mentioned it, and because the 360 degrees that we use, it dates back. It's a long time ago, and what's weird about it though is they had that, and they were actually the first group of people to solve equations of ax squared plus bx equals c. Basically, they're doing the quadratic formula. But like way back in time, before they even knew what a plus sign was, a minus sign, or an equal sign was. Hello? Hey. I can do that over in your room. Yeah. Okay, so let her put down. Let me pull that up. So let me see. I can, for starters, no, you're good. You're good. Oh, yep. I can stop.